So let's see how to calculate Clebsch Gordan Clebsch Gordan coefficients for J1 is equals to half and J2 is equals to half. So that is addition of spin angular momentum of two electrons. So spin angular momentum of two electrons. So we know that spins is nothing but for electron spin we have half, plus half or minus half. So as here there is half and half. It seems like this is only spin angular momentum. So that's why they have mentioned here spin angular momentum of two electrons. Let the spin states of two electrons be represented by xi1 of j1 comma m1 and xi2 of j2 comma m2. So in quantum mechanics the state of a particle is represented by an eigenfunction. So here they have said the spin states of two electrons. So a particular electron will be having its own spin state and that spin state is represented by this. So xi1 by this wave function, that is the first electron is described by this wave function xi1, that is a function of j1 comma m1. That is based on angular momentum of the first electron, and it is here j1 is nothing but total angular momentum. J is nothing, actually L is nothing but orbital angular momentum, S is spin angular momentum, and J is nothing but total, both orbital and spin added together, and M is nothing but magnetic quantum number. So just like we have N, L, M and S quantum numbers, that is principal, azimuthal, magnetic and spin quantum numbers, like that. So this is that, and xi2 this is for the first electron wave function is xi1, and second electron's wave function is xi2 of j2 comma, and it is a function of j2 comma m2, that is second electron's angular momentum, total angular momentum, and its orientation. So that is its magnetic quantum number. So magnetic quantum number gives idea about the orientation of the electron around the atom. Then the wave function of composite system in uncoupled representation is, so this is first electron's wave function and this is second electron's wave function if we consider individually. So composite system, so both electrons combined together, what could be the wave function they are saying? So that is nothing but xi of m1 comma m2 is equals to xi1 of j1 comma m1 into xi2 of j2 comma m2. So if we consider the two electrons as a particular system, so without coupling, that is we have coupling schemes, LSJ coupling, that is coupling between this orbital angular momentum, spin angular momentum, so like that we have. So without coupling those, an uncoupled representation, if we want to represent the state of system consisting of two electrons, this state indicates only state of first electron, this one eigenfunction indicates state of second electron. So overall for the two electrons if you want means that is this. So xi of m1 comma m2, that is in uncoupled representation. So here we are not coupling the angular momentums of the electrons. So xi of m1 comma m2 is equals to xi1 of j1 comma m1 into xi2 of j2 comma m2. So this is the combined wave function of the two electrons. As j1 is equals to half, j2 is equals to half, the possible values of magnetic quantum numbers m1 and m2 are. So here they have mentioned both are equal to half. So we know that for n is equals values we would have 1, 2, 3 and so on, and that is a principal quantum number, and azimuthal quantum number starts from 0, 1, 2, 3 and so on, and magnetic quantum number has 2l plus 1 values. So for L equals to 0 or particular L, magnetic quantum number has 2L plus 1 values. 2 into 0 plus 1, that is 3. 2 into 0 plus 1 is 1. So we are having only one value, that is equals to 0. So when L equals to 0, M value is 0. And if we consider L is equals to 1, so then we would have 2 plus 1, 3. So when L is equals to 1, M would have minus 1, 0, 1. And when L is equals to 2, 2 2s are 4 plus 1, 5. That is L is equals to 2, M is equals to minus 2, minus 1, 0, 1, 2. So we are having like this, these ion values. This magnetic quantum number values, that M. So here if we observe, magnetic quantum number values are varying by 1. So minus 1 plus 1 0, 0 plus 1 1, minus 2 plus 1 minus 1, minus 1 plus 1 0, 1, 0 plus 1 1, like that. So difference between the two values is 1. So here in the same way, J1 is nothing but total angular momentum. Only difference is this is orbital angular moment, orbital quantum number, and this is total angular momentum quantum number. So for J1 on J2 is also half we are having. Then M2 values. So 2J plus 1, if we substitute 2 into half plus 1, that is 2 would cancel. 1 plus 1 is nothing but 2. So it would have, M would have only two possible values, and those are nothing but plus half comma minus half, because here also it is varying from minus L to plus L, and difference between them is 1. Here also it is varying from minus L to plus L. So in the same way here, minus J to plus J with an interval of 1. So here minus half plus 1 is nothing but half, that's it. So we won't get 0 in this, hence we are not having 0 here. Here means minus 1 plus 1 0, 0 plus 1 1. So because of this half, we don't have 0 in the middle, and there are only two possible values, minus J to plus J. So minus J is nothing but minus half, plus 1 is nothing but minus half plus 1 is half. Hence we would have only two possible values based on this formula 2L plus 1. So that is the thing. So as J1 is also half, J2 is also half, the possible values of magnetic quantum number M1 are half comma minus half. Only these are the possible quantum number values. And now the possible values of total quantum number J is equals to J1 plus J2, or so J is nothing but total quantum number, that is total quantum number of first electron and total quantum number of second electron both added together for that particular system. It gives the total quantum number. And for J is equals to, we have half plus half, that is 1, and half minus half, 0. So these are the two possible cases, that is if we are adding L comma S, if we suppose, so we would have L minus S to L plus S values. So here we are adding J1 comma J2 vectors, so it would have values from J1 minus J2 to J1 plus J2. So J1 minus J2 is nothing but 0, and J1 plus J2 is 1 with an interval of 1. So that is the condition. So 0 plus 1 is nothing but 1. So only two possible values of J is 1 and 0. We don't have any further values for this total quantum number, half plus half 1. So as M varies from minus J to plus J, which is a difference of 1, as we have discussed earlier, the possible values of magnetic quantum number for M is equals to so possible values of magnetic quantum number for J equals to 1. So if J is equals to 1, M values are the minus 1 0 1, as we have discussed here. So J minus J2 plus J, that is minus 1 to plus 1, interval of 1. And for J equals to 0, M is 0, that is 2 into 0 plus 1 is 1, only one possible value. So if J equals to 0, M is 0, so only one possible values. So these are the possibilities. This is the main thing we need to consider first. This is the main thing we need to know first. So therefore the possible set of eigenfunctions in uncoupled representation is, so if we consider the uncoupled representation, So in uncoupled representation we are having xi of m1 comma m2, as said here, xi of m1 comma m2. Therefore the possible set of eigenvalue functions in uncoupled representation is, so xi of m1 comma m2 is equals to xi of half comma half and half comma minus half. That means if we fix m1 value to half, so m1 is having two possible values, that is half comma minus half. So first if we fix m1 to half, here also half, and m2 has two possible values, so half comma minus half. Next m2, if m1 if we fix to minus half, and m1 has two possible values, half comma minus half, so minus half comma half, minus half comma minus half. So these are the possible combinations of m1 comma m2. So we are having overall four possibilities, and the possible set of eigenfunctions in coupled representation is, so after coupling, so if we don't consider the two electrons as a separate, and if we do follow the coupling schemes, then we would have wave function of this form, phi of j comma m. So here if you see, here there is separation, this is showing m1 m2, they both are different. So this is for first electron, this is for second electron, like that clearly the difference has been shown in this. But here we are having small j and small m. Small j is nothing but j1 plus j2, and small m is nothing but m1 plus m2. So both of them mixed together, coupled together. Hence it is a function of small j comma m, whereas this is a function of m1 comma m2. It is clearly showing difference between m1 first electron and second electron. This is not showing. So as we have got j is equals to 1, so when j is equals to 1, m values are minus 1, 0, 1. So j equals to 1, j equals to 1, j equals to 1, minus 1, 0, 1. And when j equals to 0, m value is 0. So when j equals to 0, m value is 0. So these are the possibilities in coupled representation. The transformation equation representing the wave function of coupled representation in terms of uncoupled representation is, so here they are saying transformation equation. So we are getting transformed from coupled representation to, that is uncoupled representation to coupled representation. So for transforming, so how to transform this uncoupled form to coupled form? So what the operation we have to do, with what we have to multiply? So that is nothing but this equation, transformation equation. So uncoupled coordinates are being converted in, uncoupled wave function B is being converted into coupled wave function. So for that, this is the thing. So phi of j comma m is equal to summation m1 comma m2 m1 comma bra m1 comma m2 jm get get xi of m1 comma m2. So like that we are having. So this form, this is the transformation form, this is the transformation equation. So the meaning of this is, wave function of this form, that is uncoupled form, is getting transformed to this form. So in order to bring this form to this form, we need to multiply these wave functions with these coefficients. So these are nothing but the Clebsch Gordan coefficients. So here it is clearly indicating. So m1 m2 form has been converted into j comma m form. So initially it was m1 comma m2 form, and it is being converted into j comma m form. So this is the main equation. So if we operate the equation by jz, so here jz, as we are having two electrons, jz is nothing but j1z plus j2z, as we are having two electrons. So if we operate the equation by jz is equals to j1z plus j2z, so we need to operate this entire equation with this, we get. So operating with jz on both sides. So operating on left side, jz phi of j comma m, and on the right hand side we are having m1 comma m2 separately, but on the left hand side we are having combined form j comma m, but they are having separately, so hence we need to separate. So j1z plus j2z, and if we apply, so we know that eigenvalue of jz is mh cut. When jz is being operated on this wave function, it gives the same function multiplied by its eigenvalue, that is mh cut. So if h cut is taken as 1 unit, so if you neglect that one, so if we keep aside by taking h cut is equals to 1, so you would have m h cut in the place of h cut 1. So m phi. So jz would operate on this wave function. It would give the same wave function multiplied by its eigenvalue. So that is the meaning. So here also the same thing happens. So first J1Z operates on this entire summation. So summation can be taken out and operates J1Z operates on this wave function. So it only operates on M1 as it is a J1Z is because of the first electron's total angular momentum, it would change, it would operate only on M1, that is magnetic moment of quantum number of first electron. So you would have M1 xi when J1Z operates on this plus M1 xi, M1 this psi plus when this operates on this wave function, we will have M2 xi, M2 this wave function along with this coefficient. So hence we are having M1 plus M2. So that is the equation. So using equation 1, obtain it is phi of from equation in the above equation. So that is so this is the overall equation. Now what we have to do is, in the place of phi jm we need to substitute this term, because in the right hand side we are having this xi, this bracket, and here also phi jm is nothing but this xi and bracket. So if we substitute this one here and we send this term to that side, so in that we can take this term as the common xi and this bracket notation, so that can be taken as common, and this summation also common. So m1 plus m2 minus m, you would have this equation. So this is the equation after solving. Since xi of m1 comma m2 are linearly independent, in fact orthogonal functions, equation 2 is satisfied if only. So here xi's are linearly independent and orthogonal functions satisfied. So we have independent terms like x, y, z equals to 0, ax, by, cz. It will, and x does not depend on y, and z and y does not depend on x and z. So if they are independent, they do not depend on each other linearly. So it is possible only when a equals to b equals to c equals to 0. Only then it would become to 0. The coefficients are 0. And when they are not depending on each other. So suppose if we have y is equals to 4x, z is equals to some 2x like that, then they are not linearly independent, they are dependent. So then we would have a comma b comma c, some values, certain terms we would have. So then these coefficients would not be equal to 0. So that is the thing. So hence here it is mentioned that a linearly independent equation 2 is satisfied if only these coefficients are is 0. So this is just like ax. In the place of xyz we are having this wave function xi, and in the place of a coefficients we are having this term, and summation is nothing but addition. So ax plus by plus cz, like that. Hence we would have this a, b, c 0. So in the place of a, this term. So this entire thing is 0 for all values of m1 and m2. So from this it is of the form ab equals to 0. So it is possible if either a equals to 0 or b equals to 0. So this gives either this term equals to 0. If we do, this m would go to that side, m is nothing but m1 plus m2, or this coefficient is equals to 0. So this is nothing but Clebsch Gordan coefficient. That is, all Clebsch Gordan coefficients are 0 for a fixed j unless. So that is the meaning of this ab equals to 0. So what they are saying is, all the Clebsch Gordan coefficients are 0 when m is equals to m1 plus m2, until m is equals to m1 plus m2. So if when m is equals to m1 plus m2, then you will not have Clebsch Gordan coefficient equal to 0. So when m is not equal to m1 plus m2, then you would have Clebsch Gordan coefficient as 0. So that is the meaning of this terms. So when this condition is satisfied, then only you would have Clebsch Gordan coefficients. Otherwise, the Clebsch Gordan coefficient is 0. So the numbers j1 and j2 are largest values of m1 and m2 respectively. So as we have said, value of m ranges from minus l to plus l or minus j to plus j. So the highest value is nothing but j or the value of l. So here also the highest value of m1 is j1 and the highest value of m2 is j2. And the largest possible value of m is, so as we already know that m is equals to m1 plus m2. So largest possible value of m1 is j1 and m2 is j2. So hence it is getting added up. Then equation 1 reduces to a single term. So in the equation 1 we were having phi of j comma m equals to bra of j1 m1 comma m2 m1 plus m2, that is m1 plus m2 is nothing but j and small j, and again the same m1 plus m2, that is nothing but small m. That means actually what is small j, that is nothing but j1 plus j2. So in the place of small j we are having j1 plus j2. And what is small m, m1 plus m2. So in the place of m1 j1 and in the place of m2 j2. So that is the thing. So if we see first equation, so phi of j comma m m1 comma m2 j comma m. So in the place of j we are having j1 plus j2, in the place of m also we are having j1 plus j2, and in the place of m1 j1, in the place of m2 j2. So first in equation converts to this form. Now using normalization condition we obtain. So normalization condition, we know that integration of psi into psi star d tau is equals to 1. So this is the normalization condition. So here also if you do normalization, so integration of phi into phi star d tau equals to 1. So if we do that, and then we would have integration of this one and its complex conjugate, and xi into xi star d tau equals to 1, as xi into xi star d tau is 1. So this one multiplied by its complex conjugate, that is nothing but we would get whole square. So a complex number multiplied by its complex conjugate gives us modulus of that particular complex conjugate number, that particular complex number. So this is equal to 0. So based on this applying this condition, so xi into xi star d tau 1, this one into this one 1, you would have only this one would be remaining. So this one multiplied by its conjugate, so that is equals to 1. And here if we send it to that side, square root of 1. So if we neglect phase factor, that is theta e power I phi, like that we would be having. So if we neglect, this is equal to 1, this term is equals to 1. So equation 4 reduces to, so this equation would reduce to, as this value is 1. So you would have phi of j1 plus j2 comma j1 plus j2 is equals to xi of j1 comma j2, as this value is 1. So you would have, from this equation you would have this one. And in the question they have already given that j1 is equals to half and j2 is equals to half. So equation 5 and 6 take the form. So if we substitute this j1 j2 values in this equation, so half 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 comma half, and here half plus half 1, half plus half 1 equals to 1, and here also half half plus half 1 comma 1, and xi of half comma half. So you would have this form. So actually this is like this. So it's just simply a function. Phi is a function of 1 comma 1, xi is a function of half comma half. So operating equation 8 by j minus, that is equals to j1 minus and j2 minus, we obtain. So just as before we have operated with jz, that is equals to j1z plus j2z. Here we are operating both sides of this equation with this j minus. So j minus of phi of 1 comma 1, and here j1 minus plus j2 minus phi xi of half comma half, as here we are having m1 comma m2. We need to remember this because we used to get confusion over here only. Here phi is a function of j comma m, small j comma small m, and xi is a function of small m1 comma small m2. So the eigenvalue of j minus is, so this formula for eigenvalue of j minus is square root of j plus m into j minus m plus 1. So this is the eigenvalue, just like we have eigenvalue of jz m h cut. So this is eigenvalue of j minus, and h cut is we have already taken 1, and the operation decreases the value of m by 1 we get. So j minus operation, actually jz operation, after operating it keeps the wave function as usual. It does not change the reduce or increase the value of m, and j minus decreases the value of m and by 1 unit, and j plus increases the value of m by 1 unit after operating on wave function. So that one we need to remember. So this would operate on this, it would give root 2 phi of 1 comma 0, and this both separately would operate, you would have this. So how is this possible is, here we are having calculation. So this is the thing we wanted to find out. So j minus phi of 1 comma 1 and j1 minus separately operating on j of half comma half, and j2 minus separately operating on j of half comma half. So now what we need to do is, so j minus, here j is 1 and m is 1, small j is 1, small m is 1. So based on this formula, so 1 plus 1 and 1 minus 1 plus 1. So 1 plus 1 2, 1 minus 1 would get cancelled, here we would have, so 2 into 1, so root 2. And what does this j minus do? It reduces the value of m by 1. So that is nothing but 1 minus 1 is 0. That one we need to consider. So this is regarding left hand side. And while doing the right hand side calculation, we need to be very careful, because we need to get confused here. So here j1 minus is being operated on is xi of half comma half. So it would, as it is 1 minus, so it would only operate on first electrons quantum numbers. So you would have j1 plus m1. So j1 in the question they have already given, so here you should not be confused. So this is m1, this is m2, but there is no j1 j2. Unlike here we are having j and m, within the wave function we can find j and m, so we can easily say this is j, this is m. But here this is m1 and m2, we don't have, in the question we have where it is given. If we want to get the values of j1 and j2, it is given in the question, so from there we need to take. So this is where the confusion arises. So j1 half as given in the question, and m1 half, and j1 minus m1, half minus half plus 1. So half plus half 1, this one will get cancelled, 1 into 1, so 1. And another important thing is j1 minus reduces the value of m1 by 1. Half minus 1 minus half, it does not do anything with this m2. M2 will remain the same, it only reduces the value of m1. And next case j2 minus, that is nothing but square root of j2 plus m2. j2 is also half as given in the question, and m2 is half, this is m2, m1 m2, half, half plus half, half minus half, j2 minus m2 plus 1. And j2 would reduce the value of m2 by 1, so half minus 1, that is minus half, it does not touch do anything with m1. So this is the thing we are having, so 1 and here also 1, so hence we would have this one, and this that's why we are having this form from these calculations. So if we send this root 2 that side, 1 by root 2, here also 1 by root 2, like that. So this is one of the equation. So now we have to represent this equation of the form of equation 1, that is of this form, phi of j comma m expressed as summation of wave functions. So like that we have to represent. So under this case equation 1 is expressed as, that is in the form of equation 1, so phi of 1 comma 0 and summation of these wave functions multiplied by the Clebsch Gordan coefficients. So that is the form. So actually what is happening here is minus half comma half form is getting converted into 1 comma 0 form. and half comma minus half form is being converted into uncoupled form is being converted into coupled form 1 comma 0. So half comma minus half getting converted into 1 comma 0. So that is the Clebsch Gordan coefficient for this, and this is the Clebsch Gordan coefficient for this. A comparison of 9 and 10 gives two more Clebsch Gordan coefficients. So this is equation 10 and this is equation 9. So here this coefficient is 1 by root 2, just like this coefficient. So that is nothing but this is equals to 1 by root 2, and this coefficient is bra of half comma minus half 1 0 get, and here 1 by root 2 half comma minus half. So this term is equal to 1 by root 2. That's because of combining those two equations. And next, so this is equation 11. So operating equation 9 by lowering operator j minus again we obtain. So again we need to continue the same thing. Again we have this equation 9. We have to take this equation 9 and we need to operate by j minus on both sides. So on operating we would get this term. So here the calculation is a little bit complex. So actually, so what we are doing, j minus on equation 9. So j minus phi of 1 comma 0 and j1 minus plus j2 minus for this. So j1 minus plus j2 minus into this term into this term. So it is like a plus b into c plus d. So we would have 4 possible terms on that multiplication. So these are the 4 possible terms we would get. So first j1 minus operates on xi of minus half comma half, and j1 minus operates on half comma minus half. j1 minus operating on this and j1 minus operating on this, and next j2 minus operating on this and j2 minus operating on this, minus half comma minus half. So these are the possible terms and we can keep these constants aside. So this is the thing. So now we need to apply that eigenvalue formula, that is root of j plus m into j minus m plus 1. That formula we need to apply for this entire equation. So if we apply, so square root of j plus m, so this is j. So here we would not get confusion, only here we would get confused with the j and m values. So here j is 1 plus 0, j plus m, j minus m plus 1. So 1 here, 1 plus 1 2, so root 2 like that you would be having. And another important thing is j minus reduces the value of m by 1, so 0 minus 1 minus 1. And next here if you see j1 minus, first of all we need to see here j1 minus would reduce the value of m1 by 1. So minus half minus 1 is nothing but minus 3 by 2. But in the question we have already considered that m has only half comma minus half values, m1, because j1 is equals to 1 means, sorry, j1 is equals to half means m1 is minus j12 plus j1, that is minus half to plus half, only those values. There are no 3 by 2 values. So if we operate this, so it reduces the value of m1 by 1, so minus half minus 1 minus 3 by 2, so that is not possible, hence this term becomes 0. And in the same way here also j2 minus will operate on this, it reduces the value of m2 by 1, minus half minus 1 minus 3 by 2, so this is also not possible, hence this terms would become 0. So now if we consider these two terms here, if you see, so j1 minus operating on this, so here j1 is always half, it would be given in the question. So this is only m1 comma m2, this is m1, this is m2, this is m1 and this is m2. So for this case if we consider, so j1 minus operating, so j1 plus m1, j1 half has given in the question and m1 is half, and j1 minus m1 plus 1, half minus half plus 1 would get cancelled, 1 half plus half is 1, hence you are having 1 by root 2 as usual. And it would reduce the value of m1 by 1, half minus 1 minus half, and this minus half would remain as usual, it does not reduce the value of m2. And again here also the same thing. So j2 minus operating on this. So square root of j2 plus m2. So j2 is half as given in the question. m2 is half, half plus half, into j2 minus m2 plus 1. So that is xi of minus half comma minus half. So that is because j2 reduces the value of m2 by 1. Half minus half, half minus 1 is minus half. So you would have this. So again this is 1, this term 1 into 1 you would have. So you would have this term. And now if you see here, xi is a function of minus half comma minus half. This is also minus half comma minus half. 1 by root 2, 1 by root 2. So it's just like a plus a. That is nothing but 2a. Hence 2 into this term. And root 2 would get cancel, and you would have root 2 in the numerator. Again this numerator root 2, this root 2 would get cancel, and finally this one would be remaining. So in that manner we would get this equation. So under this equation 1, so we need to express this of the form of equation 1. So phi expressed as function summation of functions of uncoupled functions. So here minus half comma minus half is being converted into 1 comma minus half. So minus half comma minus half converted into 1 minus 1 comma minus half. So this is the Clebsch Gordan coefficient form. So comparing 12 and 13. So this is 12th equation same as this, and 13 if you see here there is nothing, is there is 1. So this is equal to 1. This is also another Clebsch Gordan coefficient. So keeping in mind that orthonormal linear combination of an equation having non-degenerate states decreases the value of j by 1, the orthonormal linear combination of equation 9 is expressed as. So orthonormal linear combination having decreases the value of j by 1, equation 9 is expressed as. So this is equation 9. So here j value is 1 and m value is 0. So already we have phi of 1 comma 1, phi of 1 comma 0, and phi of 1 comma minus 1. So only term exited from this is phi of 0 comma 0 from all the possible combinations. So we have got all these three combinations. This is missing. So orthonormality they are taking, considering. So orthonormality condition is nothing but xi integration of xi I xi j d tau. It would be equal to 1 when I equals to j, and it would be equal to 0 when I is not equal to j. So that is the orthonormality condition. So here, so they are saying it reduces the value of j by 1. So here j value is 1 and m value is 0. So in this condition j value is reduced to by 1. 1 minus 1, 0. And if we do integration in this manner, integration of xi I xi j star d tau, it would has to be 0. We have to get 0. So if we do this one and this one, multiply their conjugate of this one and this one, conjugate of this function with this normal function, and if we do integration we should get 0 is the possible thing. So in that we would multiply this function with this function. So if we do conjugation also, this 1 by root 2 would be same. 1 by root 2, 1 by root 2 would remain same. So it has to be designed in such a manner that multiplying this two we should get 0. So hence xi of half comma minus half, that is this. Here it is 1 by root 2, here also it is 1 by root 2. So 1 by root 2 into 1 by root 2 you would have 1 by 2. And here xi of minus half comma half, here also xi of minus half comma half. Here it is 1 by root 2, but this is minus 1 by root 2. That is where the difference comes in the both. Minus 1 by root 2 y means 1 by root 2 into 1 by root 2 half. Again minus 1 by root 2 into 1 by root 2 you would have minus half. Half minus half equals to 0. So in order to satisfy this condition, this function multiplied with this function, we should get 0. So in such a manner we are designing coefficients over here. Actually wave functions are the same, minus half comma half, half comma minus half. So minus half comma half, half comma minus half. So only thing we are changing is coefficients. So we need to design in such a manner that the product equals to z, we should get 0 in such a manner. So another thing is, just like for everything we have applied j minus. So here also j minus we have applied to get from phi of 1 comma 1 to phi of 1 comma 0, from phi of 1 comma 0 to phi of 1 comma minus 1. We have applied that one, but this is the different case. J value is getting changed, hence we need to follow this orthonormality condition here. So under this condition, equation 1 is expressed as, so if we express this phi of 0 comma 0 in the form of equation 1, that is this equation. So here half comma minus half, so this is nothing. So half comma minus half is being converted into 0 comma 0. So hence half comma minus half 0 comma 0, and minus half comma half is being converted to 0 comma 0. So minus half comma half 0 to 0 comma 0. So that is the thing. So comparing 15 and 16 we would get, so if we compare this equation with that equation, so in the place of here we were having 1 by root 2, and in the place of this we were having minus 1 by root 2. So these are the Clebsch Gordan coefficients. So equation 7, 11, 14, 17, so these equations what are all we have found out now represent all non-vanishing Clebsch Gordan coefficients for the case j1 is equals to half and j2 is equals to half. So these are the non-vanishing, that means they are not 0, they are having certain value. So these are the Clebsch Gordan non-vanishing coefficients for the case. So if we found out that one is enough, because remaining are all are vanishing, that is 0. Remaining are all Clebsch Gordan coefficients, that is based on this function initially which we have found out. So the matrix representation of the Clebsch Gordan coefficients may be expressed as, so finally in order to represent this Clebsch Gordan coefficients in the matrix form, so that is this form. So at the top we are having j values and m values, corresponding m values, and here we are having m1 comma m2. So this is uncoupled form and this is coupled form values, uncoupled form values, coupled form values. So m1 comma m2 to j comma m. So this coupled form, uncoupled form is being converted to coupled form. So that is nothing but Clebsch Gordan coefficient. So in the matrix form, so for j equals to 1, m value j equals to 1 1 minus 1 0 1, we are having this many 3 possibilities. So j equals to 1 minus 1 0 1 m values, and for j equals to 0 you are having m equals to 0. That is because of this ones has to be like this, ones we are having, so it has to be kept that form. So that, and here m1 m2 possible combinations. So this is half, this is half. So if this is half, this is plus half comma minus half. So when this is minus half, this is plus half comma minus half. So 4 possible combinations. So in matrix form, so now how to represent is, when j comma m is equals to 1 1, then m1 and m2 Clebsch Gordan coefficient, that is for half comma half is 1, that is from this equation, this phi value j comma m values 1 comma 1, so 1 comma 1, and psi of m1 comma m2 values half comma half, so half comma half. So here the coefficient is 1. So remaining all coefficients are 0, as they are not indicated in this equation, because a plus 0 plus 0 plus 0 is nothing but a. So remaining all are 0. So like that. And next for phi of 1 comma 0, that is this. So we are having 1 by root 2 for minus half comma half, 1 by root 2 minus half comma half, this term, and again the same 1 by root 2 for half comma minus half comma minus half 1 by root 2, and there are no remaining wave functions, remaining possible wave functions, so they are all 0, so 0 0. So like this, if you go in the same manner for phi of 0 comma 0, and this is for phi of 1 comma minus 1, so phi of 1 comma minus 1 minus half comma minus half, remaining all are 0, hence minus half comma minus half 1, hence we have written this 1 comma minus half at the end but not here, so then this one is here like this, so remaining all 0 like that, because it would be easy to see. So this is the it looks like an orderly form. So this is the Clebsch Gordan coefficient matrix form. By the help of this matrix, we may represent the transformation from uncoupled to coupled representation by matrix equation. So the transformation equation now we need to consider, that is this equation. This is the transformation equation. So this equation can be represented in the matrix form as follows. So here we are having phi of 1 comma 1 1 comma 0, that is this value, phi of 1 comma 1 1 comma 0 0 comma 0 1 comma minus half, and xi value, xi of half comma half, xi of half comma minus half, same order minus half, and multiplied with this matrix. So that is the matrix. So by multiplying this one with this one, we are getting these forms. So if you see phi of 1 comma 1 by taking the form of corresponding elements, so this element would multiply with this element, and this one, it is 0 0 0 plus plus plus, so then we would have xi equals to, that is phi of 1 comma 1 is equals to xi of half comma half, so we would have this form. And in the same manner, phi of 1 comma 0, if we see, so 0 into this one 0, so half into this one, so that is 1 by root 2 into this one, and 1 by root 2 into this one plus, and this one would be 0. So this is nothing but a representation of this equation. So these equations can be represented in this matrix form. So this is the form of expressing, matrix form of expressing this Clebsch Gordan coefficients. So this is the calculation of Clebsch Gordan coefficients for J1 is equals to half and J2 is equals to half. So thank you.